Hello everyone, and welcome to lab number 1 of our falling mass rotating pulley experiment. Now, today is going to be a little bit different. Right? So, as I mentioned in the outro video for class on Tuesday, right, part of the scientific process, the process of doing experiments, is developing testable models and thinking about what effects might and might not matter. So you're going to be doing a lot of that work today, and so today is going to be a little bit more theory heavy than it might be otherwise. Okay, so you have in your lab manual, right, sort of the goals for this week. If anybody doesn't have their lab manual with them, please let me know. I will send that to you. So I just want to highlight the goals that I'm going to talk about right now. There's a couple of other things, like figuring out how to insert equations into your favorite word processing program that I'm confident you can figure out on your own. If you need any help, please let me know. But here are the things I'd like us to think about today. Goal number 1 is going to be for you to go and refine our model to add terms for air drag. So I'm going to call that F, the magnitude of that force, F sub d for force of drag, and also a torque due to friction in the pulley bearings, right? You know that this pulley is not truly frictionless because if I spin it up, eventually it stops rotating. Right. So we're going to want to think about those two effects and what influence they might have. In the model I built up on Tuesday, right, I also completely ignored the mass of the string. I assumed an ideal string, so one that's massless and inextensible. And today what I'd like to do is to actually measure the mass of that string so that we can think about how to work in a regime where the mass of the string truly is negligible. Our next thing we're going to try to account for is to estimate the size of that air drag. It turns out that estimating the drag force requires us to get a handle on the size of our masses. So we'll go and we'll measure that also. After we've done that, we're also going to want to estimate that frictional torque. And I'll describe a way that we can at least get a conservative order of magnitude estimate for it. So 5 and 6 are the two parts that I think are the most fun here. We're going to want to estimate the minimum mass we should use that's hanging right from our pulley such that the frictional, such that air resistance Fd and the frictional torque tau sub f are both negligible. I'll have a wee bit more to say about this in just a sec. The last thing that's really important for you to do is to figure out how to linearize our model. You've now built up some experience in working with linear models for data, starting with the card-on incline experiment, going through the pendulum, right? And it turns out you're going to be able to linearize the idealized model I talked about on Tuesday. Now, in the last couple of labs, I basically showed you how to linearize your model. This week, I want you to figure it out for yourself. And again, happy to chat if that would be helpful. All of this is leading to what's due for next Tuesday. There's no written homework assignment. There's only one thing due. It's a substantial thing, though. I would like you to prepare a draft of the theory section of your final lab report. And I will be providing some additional guidance on what this ought to look like. So in class on Tuesday, we talked about this idealized model for the acceleration of our falling mass. Just to remind you, here I is the moment of inertia of our pulley. Little m is the hanging mass, and little r is the radius of our pulley. Now, I like writing the acceleration in this form, which is different than what's in the manual, for the following reason. You can see that the acceleration is proportional to the free fall acceleration little g. But it's also clear to see how the acceleration is smaller than g, because the denominator here is larger than 1. And it's larger than 1 because of this term. This term that's proportional to the moment of inertia I of the pulley, or more specifically, the ratio between the inertia of the pulley and the hanging mass. Now, what you're going to do today is to work out a more refined model that incorporates frictional torque due to the pulley bearings and drag due to air resistance. This is the form that the manual asks you to derive. However, I think it's a little bit more suggestive to write it this way, as I did for the idealized model. And in order to do that, what I'm going to do is I'm going to multiply by 1 in a clever way, namely 1 over m in both numerator and denominator. And if I do that, the result I get, right, is that I get g minus tau frictional over mr minus f d over m divided by 1 plus I over m r squared. So this is really helpful for several reasons, right? So what can we take physically away from this? So notice, right? So notice, right, that the frictional torque by the pulley bearings and the drag force both decrease the acceleration, or this is, remember, the magnitude of the acceleration. The manual it isn't writing vector magnitudes the way I might prefer to do. So, and then that maybe intuitively makes sense. You can, from your experience, sliding things down ramps or sledding or whatever, it's probably plausible that friction is going to slow down how quickly this our mass is going to accelerate. And last one physical takeaway from writing it in this form. This also helps us see when these effects matter. So let me take sort of the two things separately, right? So looking at, say, just let's just look at the air drag term here, and let me circle that. Right. But now we know that, right, everything in the numerator here, right, or that we're adding and subtracting, you can only add and subtract things with the same units, and so you know that drag force divided by a mass, in fact, should have units of acceleration, right? If we want to be in a regime where we can neglect this air drag term, which is what you're going to be trying to estimate today, right? What we want, neglect, right? What we want that circled term to be much smaller than g. So what does this tell us, right? We can maybe think a little bit about limiting cases, right? If m were really tiny, right, if m were small, 1 over m would be large, and we might have a problem satisfying this requirement, right? However, conversely, if we make m large, right, the bigger I make m, the smaller this is going to be. That is precisely why I'm going to ask you to think about a minimum mass m such that this air drag term can be neglected, right? Right. So there's a minimum m for which right. That's a exclamation point, not a question mark. Right, so there exists some minimum value of the mass, a hanging mass for which this will be true, and I'm going to ask you to go and find that. And so that, in order to do that, of course, we need to think of a way to estimate this this air drag force, which we'll turn to in just a second. I now want to say something about estimating the air drag force, Fd. So the manual has some suggestions for how you might do that. And I'll talk about a little bit more what that suggestion is. So the idea is to use an expression for the force of air resistance, or the drag force exerted by a fluid on a sphere. Okay. So a long and nasty fluid dynamics calculation. I would be happy to talk to you about this maybe after you've had math methods. So shows the following. For the drag force by a fluid on a sphere of radius a, it turns out that the drag force has a magnitude of 6 pi eta, which is AV. In other words, the drag force is linearly proportional to how fast the sphere is moving. So let me unpack that. So this is the speed of sphere. Right? So here, right, is A is the radius. Eta is a new thing. So eta is what we call the viscosity. The probably the most intuitive way to think about viscosity is in terms of that's how we describe the thickness of a fluid. So take for example, right? So air has a pretty low viscosity. Water's got a higher viscosity in terms of, if you swim, or if you've ever stirred a bathtub, right? It's if I try flapping my arms in the air, right, there's not much of a drag force. But if you go into your bathtub and you try doing this in the water, you're gonna tucker yourself out sooner or later, right? And then things like honey or motor oil, right, have a very high viscosity. The units of viscosity. So the units of viscosity are Pascal seconds. Okay. And a Pascal is the unit of pressure, so it's a force per unit area. So if I were to unpack this a little bit more, so it's force per unit area, so that's a Newton, which is a kilogram meter per second squared over area, so that's meters to the -2 times seconds. And if I combine things, right, I have kilograms, meters to the -1, and then seconds to the -1. So the viscosity of a fluid is something you can look up online or in engineering handbooks. For us, right, we are dealing with something that's falling through air. Now, there are several ways in which this is a really approximate or sort of result for estimating. One sort of maybe apparent way and one way that's not so apparent. First of all, I showed you the mass and hanger last time. Was it a sphere? No, it's not a sphere, right? If you kind of think about it, it's maybe sort of like a disk, but it's also got that bar on the side. I don't have it right this second, but I think you remember it wasn't a sphere, right? Fluid dynamics calculations are, in general, pretty hard. I am certain there's no way to exactly calculate analytically the drag force on something of that shape. You would need to use probably some finite element computations and a computer to do it. So it's not spherical, but there are ways in which we can model something as a sphere, at least to get a rough order of magnitude estimate. Right? The old joke about physicists and spherical cows does carry a bit of weight. The other way in which this equation is, we should take this with a grain of salt, is that in some sense it's flat out wrong for the situation we're talking about. So namely, so this is not obvious, but so it turns out that this is only valid for several things that have to be true, right? The speed of the fluid has to be slow. So let's see, that's so it requires that the size of my object times how fast it's going, and the viscosity and the density. So rho is the density of my fluid, A is the size of the object, V is how fast it's going, and eta is my viscosity. It's only really valid when this ratio, which it turns out is dimensionless, is much less than 1. If you like fluids, and I'd be happy to talk to anybody who's interested about it, this turns out to be a dimensionless quantity combination of factors called the Reynolds number, which is usually given the symbol Re. So just quick aside, it turns out that the fundamental equations of fluid dynamics, which is called the Navier-Stokes equation, is impossible to solve analytically in any non-trivial geometry exactly. If you take a fluids course, what you basically learn how to do is to solve Navier-Stokes under different sets of assumptions, when you can neglect different terms in the equation, and you hope that you can sort of stitch things together to gain some intuition about what happens in intermediate regimes. Sort of the key parameter that governs what terms in Navier-Stokes you can neglect is none other than the Reynolds number. Low Reynolds number flows are really, really cool. They matter a lot in my research. They mean that things like bacteria and microorganisms live in a totally different fluid universe than we're used to. There's some really mind-blowing things I'll have to tell you about another time because we're getting sidetracked. But the point is, this equation is only valid in the low Reynolds number limit. And if you go and run the numbers, I think you can convince yourself that we are not, in fact, at low Reynolds number. Now, that's kind of okay in the sense that whatever we calculate with this is going to be wrong. But it was going to be wrong anyway because our mass is in a sphere. We can still, however, use this as a basis of an order of magnitude estimate. Okay. So wrong, but okay for order of magnitude. And here we'll just have to, just like you've done in other classes, we'll have to do the best we can, and, rather than throw up our hands in despair, and do the best we can to make an order of magnitude estimate. Now there's one more thing about that, right? In order to calculate this force, you need to know how fast the thing is going. But we don't know how fast it's going. We haven't done the experiment yet, right? There are some things, though. I claim that you have the wherewithal to make an order of magnitude estimate, or at least set an upper bound on how fast something can be going, right? So if we drop our mass, and you've seen, I think, how tall our pendulum stands. It's something like 1.5 meters. If I can put this up on I don't think I can, it's too big and heavy to put up on like a good table without like, I don't want to like ruin our dining room table with this thing, so like it'll probably end up, the mass will probably end up dropping 1.5 meters, maybe 2 meters tops if I can find something to prop it up against. But if you have something that drops a distance of, 1 or 2 meters, I think you can use what you know from intro physics to estimate sort of how the maximum possible speed that it could possibly be going after being released from that height from rest. I'll let you think about it, and if you're really, really stuck, come talk to me and I'll give you some more hints. So I now want to say something about the minimum mass we want in our experiment, right? Because we want to be able to ignore some of the non-ideal things we've been considering. Namely, we want to be able to ignore the mass of the string, the frictional torque by the pulley bearings, and air drag. Right? So what we want in particular is we want the mass of the string to be a lot smaller than the mass that we're using. That's sort of the idea of having this minimum mass. And in the manual, right, we suggest that you try to work this out to like a 1% level. So in particular, we want string to be less than 1% of the total mass. So in particular, we want this less than 0.01 times our hanging mass m. And if I go and measure what the mass of the string is, as I will do in a sec, we can go ahead and calculate what the minimum m is that satisfies this inequality. Let me just rewrite this with epsilon being my small quantity so that I don't have to keep writing the number over and over again. The same kind of idea, right, applies to all the other things. In particular, right, for our drag force, right, remember we said when we were looking at the refined model for the acceleration, right, to neglect Fd, right, we want that to be small, so we want g, our free fall acceleration, to be much larger than Fd over my mass. I can sort of use this sort of idea here in the same sort of way as, so if I have that epsilon being like 0.01, or I want epsilon times this, times little g, to be larger than Fd over my mass. So once again, if I go and I estimate my Fd, right, I can go and calculate the minimum value of m that satisfies this inequality. Now, what I'm going to do is I'm going to leave a forum thing, a forum post open on Sakai. I don't want to give away the answer here. I want you to think about what we're going to do today. I would like to encourage a robust discussion and debate, hopefully about what minimum value of m we ought to use. And then I'll use that to help me figure out how to do this experiment. So what I will do now is I'll end this video. I will next, in the next video, we'll talk about measuring the mass of the spring and the size of the hanging mass. We'll do another video where we measure the frictional torque by the pulley. Oh yeah, I forgot, which I've got right here. And then I'll also make another video and give you some comments about what should go into a well-written theory section for your formal report on this experiment.